Okay. Now we are going to discuss we are going to establish, rather we are going to derive the Onsager reciprocal relationship through a chemical kinetic scheme. Basically, we will be using the principle of detailed balance. We'll come to the point what is the principle of detailed balance in due course. Okay. So it is a lengthy discussion. We may divide it into two parts at least. So to start with, here we use a chemical kinetic scheme to gain insight to the origin of the Onsager reciprocal relations. Of many applications of non-equilibrium thermodynamics, to various chemical processes, the application to the chemical kinetics is exceptionally limited in practice because of the requirement of the flux flow force relations be linear. So as we are in the linear flux force regime, but most of the chemical kinetic scheme they are not linear. So in most of the cases, the version of the non-equilibrium thermodynamics we are studying that is not applicable. So here to do that we need to stick to the simple linear flux force relation. Okay. So nevertheless, in this section, we will see how the Onsager reciprocal relationship arise by studying a simple chemical reaction. But keep in mind, in normal chemical kinetics, the Onsager reciprocal relationship or the thermodynamics, non-equilibrium thermodynamics we are studying, it is very limitedly applicable. So let us start with a reversible first order elementary reaction as described by x goes to y, where the rate constant for the forward direction is kxy and that's for the reverse direction is kyx. So though this reaction is too simple to involve Onsager reciprocal relations, still we can use it to introduce some simple reaction, some simple relations. I think I have written it reaction, it should be some simple relation, some simple relations. Still we can use it to introduce some simple relations, and notation which will later be useful. So the rate constant of the reaction is given by dx by dt equal to minus kxy into concentration of x plus kyx into concentration of y. That is the simple expression for the rate constant, as you know, where x within third bracket and y within third bracket are the concentrations of x and y respectively. So next come to the second page. We can define the flow of reaction from left to right, that means going from x to y, that is the flow of reaction from left to right, that is j equal to minus dx by dt or plus dy by dt, that is conventional. So which will be equal to minus kxy into concentration of x minus kyx into concentration of y. So now at equilibrium, what will be? At equilibrium j equal to 0, because there will be no net flow of reaction from left side to right or right side to left. So as a result, equation 2, that is this equation, becomes what? K. So that is j equal to 0. So in that case, kxy into x at x equilibrium concentration equal to kyx minus yeq, that is the equilibrium concentration of y. So now we can define two quantities, alpha x, that is how much x has already reacted, that is alpha x equal to, that is the extent of reaction, you can say, that is concentration of x minus concentration of x at equilibrium. Similarly, concentration of alpha y is defined as concentration of y minus concentration of y at equilibrium. So it can be noted that alpha x plus alpha y equal to 0. So if you add alpha x and alpha y, it should be 0, because total concentration of x and y at any point must be equal to the total concentration of x and y at equilibrium. So alpha x and alpha y must be 0. So as y equal to xeq plus yeq. So now from equation 2, that is this equation, we can go ahead and find that j equal to kxy into x minus kyx into y, or in place of concentration of x we can write concentration of x is alpha x plus xeq and concentration of y is alpha y plus yeq. So we can substitute concentration of x by alpha x plus xeq, and here concentration of y by alpha y plus yeq, and go ahead and find that j becomes alpha x into kxy plus kyx. So this is a very important relation. We will need it again and again. Keep it in mind. Okay. So this is true because alpha x equal to minus alpha y. So where we kept in mind, we have used this fact that alpha x equal to minus alpha y or alpha x plus alpha y equal to 0, and kxy xeq equal to kyx at yq because of this thing we have used, this thing. So this is equal to this as discussed before. So if this reaction system is isolated, then d equal to, from thermodynamics first law, d equal to TdS, that is dq equal to TdS. So d equal to TdS minus PdV, and for open system mu x dnx plus mu y dny. So then at constant u and v, so that means dv equal to 0 and d equal to 0. So in that case TdS, and as the system is isolated, total S will be S prod. So TdS becomes minus mu x by dnx minus mu y by dny, or ds prod equal to minus mu x by t into dnx minus mu y by t into dny. So now we come to page number 3. So dividing the above relation by dt, we find that ds prod by dt, that is equal to s prod dot equal to minus mu x by t dnx by dt minus mu y by t dny by dt. So now dividing both sides by v, the total volume, we get s prod dot by v equal to minus mu x by t into dx by dt, because nx, the number of mole, divided by volume is the concentration. So concentration is nothing but the number of mole by volume. So that is the constant, that if you divide this relationship by v, total volume, it becomes concentration of x. So this becomes concentration of x and this becomes concentration of y when you divide by v. So as a result, you get s prod dot by v equal to minus dx by dt into mu x by t minus dy by dt by mu y by t. Once again, dy by dt equal to minus dx by dt, so equal to j. So that is s prod dot by v becomes minus dx by dt into mu x by t minus mu y by t. So this is once again an important relationship. So in this equation, this is the fundamental entropy production relation here. So for this purpose, to derive Onsager reciprocal relationship, this kind of fundamental entropy production equation will be used. So we can write equation 3 as s prod dot equal to j into a, because there's only one flux, only x is flowing towards y, so there's only one flux. So s prod dot by v equal to j into a. So where a can be identified as this and j is this already defined. So where j equal to minus ds by dt, that is equal to dy by dt, and a, the affinity of reaction, so mu x by t minus mu y by t. So this is the difference in the chemical potential divided by temperature will be the force for reaction, that is the reaction affinity of reaction. So this a is called the affinity, which is the force for the reaction to occur. So now the linear flux force relationship, so there's only one flux and one force. So the flux is only j, so j equal to L into a. So or a is already we know, that is minus mu x minus mu y by t. So L into mu x minus mu y by t. So experimentally, the linear relationship between j and a, as in equation 4, is valid only for very small value of a by r, where r is the molar gas constant. That means when the reaction is very close to the equilibrium, that we will eventually see. Okay. So now let us come to the next page. This means that concentration of x and y must be close to the equilibrium values, because mu x equal to mu y, that is only at equilibrium. So it can be shown that a, the affinity of reaction, that is what is that a equal to mu x by t minus mu y by t, or mu x minus mu y by t, that is equal to r into alpha x by xeq minus alpha y by yeq, or this is equal to r divided by kxy kyx yq alpha x into kxy plus kyx. So that can be shown. So that is true if and only if alpha x by xq is very less than 1 and alpha y by yq is very less than 1. That is, this is possible only when the reaction is very close to the equilibrium. Anyway, so we need to establish a equal to this or this. So that derivation is here. You can find, I have worked it out for you. Okay, clearly worked out. So mu x by t equal to what? Mu 0x by t plus r ln x, where this is remains here mu x by t plus r ln. What is concentration of x? X means alpha x plus xq. So we substitute x by alpha x plus xq. So now we add r ln x and subtract r ln x. So that means this divided by xq and plus this. So mu x plus this term r ln xq plus r ln alpha x by xq plus 1. So if alpha x by xq is very less than 1, that is ln 1 plus x is very close to x. If x is very small compared to 1. So in that case, if alpha x by xq is a very small quantity, we can get out of this logarithmic sign here and write it straight away as alpha x by xq. So when that is only possible when alpha x by xq is very less than 1. So as a result, we get alpha x by t equal to mu 0 x by t plus r ln xq plus r alpha x by xq. Similarly, mu y by t will become mu 0 y by t plus r ln yq plus r alpha y by yq. So now the difference between them, that is mu x by t minus mu y by t, will be this minus this. So that I have written here. So now if x is very close to xq, that is when the reaction is very close to the equilibrium, and y is very close to yq, then naturally the chemical potential of them will be very close to each other, because at equilibrium the chemical potential of x and y must be same. So as a result, you get mu x by t minus mu y by t is very close to mu x by xq minus mu y by yq, because this thing and this thing and this thing together becomes mu x close to xq, and this thing becomes mu y close to yq by t. So they are again quite close, so that will vanish. So what will remain? The remaining terms will be r into alpha x minus r into alpha y by yq. That is the thing I have written over here. So now come to the last page of today's discussion. Again, r equal to alpha x, so that we have already established in the previous page. R equal to alpha x by xq minus alpha y by yq. So we can just rearrange it a bit. R into alpha x 1 by xq plus 1 by yq, because alpha x equal to minus alpha y. So or r alpha x by yq, we take yq common, so we get this, and once again r alpha x by xq, this yq by xq equal to kxy by kyx. From, I think it's in page number 2, we have already found it out. So naturally this becomes this plus 1, or you can rationalize it, r into alpha x kyx by yq into kxy plus kyx. So as a result, the affinity A becomes mu x minus mu y by t equal to r alpha x by xq minus r alpha y by yq, or the same equal to r alpha x by kyx into xq into kxy plus kyx. So now we come back to the point. So now substituting this expression of equation 2, the expression of A in equation 4, we have already written. You look at equation 4, what we find out there, J equal to must be L into because in place of A we can write this, so we write this thing. Once again, J already we know that is equal to alpha x into kxy plus kyx. So J is this, so that means L must be the reverse of this. So L must be kyx into yeq by r, or kyx into yeq is nothing but kxy into xeq by r. So L becomes kyx by yeq by r, or equal to Lyx or L kxy into xeq by r, where L is the phenomenological constant for only one force. Okay, so this is the simple relationship and notation we have established in case of a very simple reaction x goes to y. Okay, so using this relationship and notation, we will proceed further with a relatively complicated scheme, and finally we will establish Onsager reciprocal relationship sometime in the next class. Okay, thank you very much.